So, if it's not convection currents, not that we've really spoken about what they are, and to be honest, I'm not really going to do that. Your teacher may tell you that convection currents are what drives plate tectonics, but they're wrong. It's not their fault. It's in half the textbooks. It's even in the curriculum, like I pointed out before. So, the theory that plates move because of convection currents, like I said, is false. It's not heat loss, it's gravity. Okay, we did notice that at the edges of oceanic crust, when it had those blue colors, is much, much older. Now, what do we know about the temperature when the magma is coming out to form basalt at the mid-ocean ridges? How's that temperature going to compare to the older oceanic crust, which has been underwater for 200 million years at the bottom of the ocean? And it's also, how is its density going to compare? It's been, again, under 8 kilometers of ocean for 200 million years. What's that pressure going to do to the density of those rocks compared to the new, younger rocks that are just coming out? Well, the older rocks are going to be far denser. Anyway, we will get to that. So, the crust on Earth is made up of an assemblage of tectonic plates. They've got names. These are the major ones. There are other ones. But essentially what we have here are plates which some of them move together, most of them do not. So we've got the Australian plate here and the Indian plate. Currently the Australian and Indian plate are fused together and they're moving together, though there is a lot of stress through this region, which may break up at some point. Essentially they're moving in this direction, and the Indo-Australian plate is crashing into Southeast Asia, and you may have heard of the Himalayas, which is right on that plate boundary. So as this plate crashes into the Eurasian plate, where else are the rocks going to go but up? Because it's all continental crust. It's probably not too hard or too much to expect you to be able to remember these. This is pretty cool here. Look at New Zealand. Some of it's on the Australian plate, but some of it's on the Pacific plate. Crazy. So we look at the movement. Like I said, Indo-Australian plates moving together. So now in this diagram, they've just combined them together. We can see that the Pacific plate's going in two different directions here. You can see that these plates are coming apart. You can see that these plates are going opposite directions, kind of sliding past each other. These are coming apart here. We can see that these are coming together. And notice when we've got plates coming together that we have this green with arrows going around. So they're called converging boundaries. Converging means move together. Diverging boundaries are these browny orange ones. Diverging means moving apart. Dotted lines of movement not known. It's at the bottom of the ocean and it's kind of messy. It's hard to tell. Again, this is geology. Nothing works absolutely neatly and perfectly. Transform boundaries. Okay, so there's a transform boundary there. There's also a transform boundary here in New Zealand. There's a transform boundary up here. There aren't too many plate boundaries that are transform. And what transform means is that they're moving in opposite directions, kind of sliding past each other. Not towards, not away from each other, but past each other. Again, not perfect. These ones are slightly moving, looks like slightly moving away from each other at that particular point. So this is a velocity per year. We can see that pretty slow, aren't they? Centimeters per year. It's hard to find, strange enough, it's hard to find this data. Would have thought it would be a perfect list somewhere. Maybe there is now, I don't know. This is the region where the Indo-Australian plate is breaking up. Got a lot of earthquake activity going on there. So three main types of boundaries, but there's actually four because none of it happens perfectly. So convergent coming together, divergent moving apart, convergent coming together, and transform sliding across each other. Now again, none of this is happening perfectly. So when these two are coming together, they might be sliding past each other a little bit. When these two are coming apart, well, that's the one most likely to be perfect. But there'll be different plate movement maybe down there and up there as it pulls apart. So it's not perfectly, but we'd still call it a diverging boundary, converging boundary, and transform boundary, with the understanding that most of them are combination. It's not happening perfectly. So what happens to the crust at each of these boundaries. So let's look at this diverging one. What's happening to the crust? So we've got magma coming up. So we're creating oceanic crust there. As the plates diverge, new crust is formed in the middle in the form of basalt, oceanic crust. So converging means that we've got crust crashing and actually disappearing. It's going back into the mantle. So we're destroying crust. Here, we're not destroying the rock. It still exists, but it's no longer crust. It's now become mantle. And again, lots of earthquakes along here. And that makes sense, isn't it? When we got two tectonic plates coming together, shouldn't be any surprise that there's lots of earthquakes involved. Now, when we've got them sliding past each other, technically it's not true, but we would say that the crust is preserved. Some new crust can be created because it can result in volcanoes. But what we definitely do is have a lot of earthquakes, but they're shallow, they're right at the surface. So in fact, these transform boundaries more dangerous than these ones. Even though the forces involved having these plates directly smashing into each other is greater, the earthquakes are far deeper. These ones are right at the surface. Convergent plate boundaries. So crust is destroyed, subduction zones or regions of uplift. So continental collision, so mountain building like the Himalayas, where the Indo-Australian plate is crashing into the Eurasian plate. Subduction zones. Now, subduction zones are when one plate goes underneath another plate. So, where is their convergence? You should be clever enough to realise it's all the green ones. That's where plates are moving towards each other. So looking back to the density, we can see 3.3. So we can see oceanic crust and the upper mantle, pretty much the same density. So old oceanic crust will sink into the mantle if it gets an opportunity. Now a real opportunity can happen if it crashes into continental crust. If it crashes into continental crust, which is less dense, the continental crust kind of sits on top and pushes the oceanic crust downwards. And because the oceanic crust is a similar density to the upper mantle, it will go in. Because there's the pressure, it's pushing it down. Just like if you have something that's the same density as water and kind of just floating on the top, you push it down with your finger, it'll go down without any trouble at all. Well, the thing with continental crust is once it starts going downwards, it has momentum and it keeps going until maybe it reaches a point where it snaps. Volcanoes form above subduction zones. So some people will just explain it as the subducting slab or the oceanic crust going downwards, melts and then comes up in volcanoes. It's not true at all. We'll have a look at the next diagram. So we can see the oceanic crust is going down, it's denser. This continental crust, when they crash together, it sits up, oceanic crust goes down, it pushes it down. Now the fact that this plate keeps moving means that it's going to go under. And it is gravity. So it's actually a subducting slab which is pulling the whole plate behind it. Once this process starts, it gains momentum more and more and more. Eventually, when it's hanging over the edge, too much, just like if you've got a really, really long plank of wood and you're putting it over an edge, it starts bending, bending, bending. Eventually, it'll snap if it gets out long enough, simply under its own weight. This happens to a subducting slab and it'll snap. It'll snap at some point and then come back up because it's no longer got the momentum downwards, and subduction will stop, and it means this plate movement will stop. The subducting slab dehydrates. Okay, so the subducting slab being at the bottom of the ocean has lots of water in it, has lots of dissolved oxygen and carbon dioxide because ocean water does. What happens as it gets hot, all of these volatiles leave the subducting slab. So this slab isn't melting. What it is, it's releasing all of these things. Now, above that, so it infiltrates the continental crust above it. Now, if you add water to rock, it lowers its melting point. So if you've got hot rock that's already really hot, and then you lower the melting point of that, you're not changing temperature because this is really hot, there's fluids, so it begins to melt. So we have volcanoes above subduction zones. So at about 50 kilometers, so subducted basalt, so that's oceanic crust, gets subducted. So this is just basalt. That is not basalt in the middle, that green thing. That's basalt. So we know that heat and pressure will turn an igneous metamorphic or sedimentary rock into a metamorphic rock, or a high grade of metamorphic rock. Black basalt will turn into this stuff called eclogite. Eclogite is denser and more suited to the environment in the mantle. This is a bit of mantle rock. This green thing's a peridotite. So olivine is the mineral, peridotite is the rock. That's a mantle rock that when this basalt punched up through the mantle, then through the crust, it carried little bits of mantle with it. So this is one of those samples that we get at the surface. They're pretty common. This one was from Cooma in New South Wales, where there was hotspot magmatism. So there was hotspot under there and it was pushing through the crust. There was a lot of metamorphism in the area.